Okay. I have some particle undergoing uniform circular motion. Could be a ball on a string, could be an electron circulating in a magnetic field, could be a moon orbiting around its planet. Whatever the instance is, it's uniform circular motion, so we know some special properties that the motion is going to have to satisfy. So some things to observe from the drawing. At position R1 from the center, the velocity of the particle is tangent to the circle. So I have vector v1 representing the velocity there. And then after it's gone through a little bit of a rotation, small angle delta theta, at a radius r2, and has a velocity v2, still tangent to the circle. And so this velocity vector is rotating its way around, showing the direction that the particle is moving is changing. And if it's uniform circular motion, the rate that that velocity vector changes direction has a special value. So some things to observe are this for uniform circular motion, that the radius is constant, so r1 equals r2, the speed is constant, so the length of the velocity vector v1 is the same as the length of the velocity vector v2, and I want to take those two vectors and arrange them so they are tail to tail. So v2 is like that. And the initial velocity v1 points like that. And delta v1 minus v2, so point like that. And the main reason I wanted to draw this out is that as the velocity vector is changing direction, that corresponds to an acceleration that points in towards the center of the circle. In your textbook, this is called the radial acceleration. If you're used to like an older textbook, you might know it as the centripetal acceleration. But for uniform circular motion, the radial acceleration is going to have a particular form. So if we look at how big delta V is, it's as big as one of the sides of the triangle, and then I don't need to worry about the sign of the rotation, but the magnitude of how much the velocity vector is rotated through, which is also how much the particle is rotated through. So delta V is going to be the speed times delta theta. Delta theta we can rewrite as the angular speed, absolute value of omega, over a time interval delta t. So just looking at the magnitude of things, not worrying about signs, whenever there's uniform circular motion, you have a radial acceleration that is delta V over delta t. Delta V over delta t is going to give me the speed times the angular speed, and then I can rewrite that in a couple ways because the linear speed is going to be r omega. So I have these relations in terms of three different variables. I can rewrite this a few different ways. I can rewrite the radial acceleration as v squared over r. I could also rewrite it as omega squared r. So, having uniform circular motion, radius is constant, the speed is going to be constant. Because the velocity vector is being rotated at a constant rate, there's a acceleration that's constant in magnitude. And we can write it out as whichever is more convenient for the problem at hand. Radial acceleration is v omega, or the radial acceleration is v squared over r, or the radial acceleration is omega squared times r. And those are all equivalent.